begin by thanking the organizers for inviting me here, as well as actually for the also for accommodating this kind of CMB day. I mean, this into the workshop, and I would like to talk about a proposal that we have put together. And first of all, the news is we do have an Indian Cosmology Consortium set up last year, early last year, and we made a proposal for a comprehensive next generation CMB space mission to ISRO. And so I'm speaking on behalf of this consortium today. So I should first point out that there are quite a number of people. The community in CMB from the time I joined in 2000 to now is quite radically different. There are lots of reasonably medium to senior people, some postdocs coming back at various places in India. Largely the science, but we are also seeking to address the instrument part of it if we have a program going forward with this. So the next generation CMB mission, why? I think Francois mentioned that we haven't extracted everything that we could from the CMB sky. Certainly the CMB polarization, we have only a small fraction of the information, and that itself is a rich pot that cosmology does need to do. And in doing so, there are scientific promises which are ultra high, which is revealing the signature of early universe inflation, which is gravitational waves of quantum origin. High science goals, neutrino physics, we could tell you the number of species, total mass, hierarchy, map all the dark matters, most of the baryons in the universe. Then there's legacy science, which for Planck, if you realize, half the papers were on legacy science. And that sort of is essentially, we nailed the cosmological model by a huge factor of 10 million, improve the constraints in a much bigger kind of space of parameters, rich galactic and extragalactic astrophysics. And of course, there's always this question of unique discovery, right? So what this more for the Indian in agencies, when I'm talking about, this is kind of, in my opinion, a very balanced impact to returns proposal. We have range of possibilities, pathbreaking science, high value science, legacy. On this side, if we do this, we could be seeding frontier programs in certain areas that are very critically lacking in India, promoting technology in Indian labs and industry, which similar projects have done in my experience. And of course, it brings some challenges to ISRO in terms of what their capabilities are, and I hope ISRO would look at it as an occasion or opportunity to match up to the requirements of a CMB mission. And of course, there's huge amount of computing which is always underestimated, but or not talked about so much, but that itself is a major thing. I mean, if you were to do the entire computing for a next generation CMB mission, that would be quite a big task in India itself. So what we are proposing, it's something that you'll hear again and again in the next two talks, a near ultimate CMB polarization survey, this kind of 2 microkelvin arc minute, which is a number you'll hear again, over 20 bands in an extended band from what people have been had proposed last. So this is a core extended to 60 to 900 gigahertz to take in some new science that we want. We want to also have some spectral capability. We are thinking of a small spectrometer, but an onboard absolute calibrator would be fine. But this is something that these are two optional elements to our thing. This is the primary goal of this thing. We could consider some 2 years of remote after the survey. And this is the science. So science, I won't go into too many details, but you can see new science, extension, and this is how ISRO wanted us to put it. And so there are quite a few new science, the extensions, and there's supplementary science, very rich. Okay, and I'm not going to spend too much time because this will be covered. And there's of course always with such things, when you're going forward in a crossing a barrier, you would have huge discovery space. So for people, of course, in the field, this is where we are in the plot for sensitivity. So this is the E modes, the B mode. This is where Lightbird is, and relative to that, this is where two versions of our proposals are in these two lines here. And this is typically what is required for a next generation CMB mission, right, to a comprehensive one. So it will give us the primordial gravitational wave, the tensor to scalar ratio. You saw this plot from Francois. This is how Planck is. If you zoom in and look at the Stravinsky model, then we would really be able to nail that. And this is a more technical plot of the scalar to tensor ratio that can be achieved with various levels of massaging of the data. So internally, or we can use the fact that we have high frequencies, use the CIB itself, and get to these kind of signal to noises on a scalar to tensor ratio of the order of 10 to minus 3. And these are plots of the parameters constraints that we'll do. So this is the spectral index to running of the spectral index. Here is the normalization of the matter power spectrum through lensing, and the optical depth, which is quite degenerate. We will improve because we'll know the optical depth very well. Neutrino masses, and also the epoch of reionization. And then there is very exciting science that can come from the fact that you saw a version of this is probably an older release of the projected lensing potential map. Francois showed you the final one. And this is the first map of the distribution of matter in the universe, integrated distribution of matter of the universe based on CMB data. We're using the CMB lensing that is possible with a mission like Planck, right? So this was the first experiment to provide a full sky reconstruction. Sort of this map, as Francois pointed out, is a signal to noise one, so it reminds you of the early days of CMB itself. But there is a huge room for improvement of the signal to noise by measuring the lensing of the CMB polarization information, which has not been done too well now. In terms of CL55, sorry, this thing moved up, but the current level is somewhere here. And this is how well we'll do, which will give us kind of an ability to distinguish the total mass of neutrinos, which are these three curves at different levels of total mass in neutrinos. Complementary science, there's a lot that came out of Planck, so I'm just repeating that. So we learned about the CIB, the cosmic infrared background, which basically is all the radiation that came out of star formation in the universe. CO lines, which tells you about the cold molecular clouds in our own galaxy, the galactic magnetic fields, much more beautiful plots that exist, and dust in the galaxy. This is something that I borrowed from Tuhin, who is kind of leading this activity in India. There would be Sunavsal-rich clusters. This is again something that we have already a community working on. And Planck detected about 1,000 clusters, 1,000 confirmed clusters. We would expect to detect about 50,000 clusters of above this solar, 10 or 14 solar masses, up to a redshift of 2.5. This is the projection in our study. This is how the schematic of CMB-Bharat looks, much simplified. There are actually a primary and a tertiary mirror. But so you essentially have incoming CMB going onto focal plane. What I wanted to bring out is the technical challenge here. One of the biggest technical challenges which has been solved other agency for Planck, but would be interesting for ISRO to get into, is the fact that this is the part which faces the sun, which will be at about 300 Kelvin or probably higher. And then that is insulated out from this cold part of the mission, which is at 40 K. And then the detectors through a cryogenic chain is maintained at sub-Kelvin temperature, right? So this is something that is absolutely a capability that is required if ISRO again wants to push on many other fronts with similar requirements. And this is what it is. Here you see this FTS we put in. We're not talking about it now. So you're seeing this in the projection. So these are the broad specs of the mission. So we sort of went to the upper end of what we definitely require for a compressive thing, mirror diameter 1.5, but something above 1 is good. And then these are the sensitivities here. These are the other requirements. It's essentially a 2-ton wet mass mission, and with a very interesting focal plane. This is based on the core design with extended to by 3 frequencies. 2,400 detectors, overall sensitivity in CMB band 2 microkelvin mark minute. And this is one layout. This one which the consortium came up with, which is more inspired with the ground experiments, which has about 13,000 detectors. And these are dichroic pixels. This is less studied. This is something that we had about a few months to put in our proposal, but which can, in principle, get to 1 microkelvin arc minute. So yeah, here's the specs which would be of interest to the Space Agency directly. 2 tons of weight of wet mass, so with the propellant. Diameter 4.5, 4 meters, power requirement. This maxes out the launch capability of ISRO at this point. So we have a GSLV Mark III, which is already had a couple of successful launches, and that is what is required for this mission to succeed. So it fits into the fairing. It actually can launch it to a transfer orbit from where it will go to L2. L2, you would see this picture. So these are numbers that we estimated of the requirements of our orbits and pointing. And this is, again, you will see similar requirements from the other missions. So let me get to the Indianness of the part, Indian challenges. So there are capabilities that are challenging, which are probably beyond what we are, but not nevertheless readily achievable, which is, this is something that ISRO does for a daily living mission planning. Launch to L2 would be first time, but should be possible. We have sent things to Mars. Thermal infrastructure is an interesting area where this hot-cold separation, I don't know well enough whether ISRO has had similar things before, but this would require quite a bit of capability building in terms of being able to do that here. Of course, these are standard, more standard things. Then we also identified the capabilities that would be achieved with modest planned investments. So we think we can get into the telescopes and optics of the mirror in India. So this is largely encouraging response from the lab for electro-optical systems. Prashant from that lab is here. And so these are the things that we may take on. Of course, the science payload assembly and testing may be something we could think of. The thermal systems, depending on what exists, we may be able to take on at least the first stage of the coolers. So since there are people from ISRO on the thermal design, I just wanted to tell you again in more details that this is the challenge. So you have various materials here. This is the backplane, which is at 400 K. And then you have these V grooves, and this is the cold part of the mission. And this is kind of the temperature profile obtained, right, at different levels, at different days. This is the silicon carbide telescope optics. This aligns very well with LEOS's interest in building the capability for large silicon carbide mirrors. They have up to close to 1 meter capability now. So here I put 1.2, kind of extending it beyond, but this is something that can be done. Then there are capabilities that may be achieved with extremely, with very long-term planned investments. Okay, so that is the photon noise limited sensors and readouts in the CMB frequency bands, and the cryogenic cooling in space, right? These are things that require a decade or two of development. We just had a fruitful meeting with the SAC Terahertz group on aligned and concurrent technology development program. So we could launch such things with a long-term goal of achieving them. But most preferred route would be to do this with international, get it from an international collaboration partner. But we could take on quite a bit of this in terms of detector testing and calibration facility. So this is a view of the cryogenic cooling chain, which you will see in next plots. Of course, there are benefits of making this medium and long-term strategic investments, which we put in our proposal, and they are pretty obvious. But just capacity building, nanofabrication, maybe. These are actually there are big initiatives been taken in India to expand on this at a national level, and we'll be one good reason to do that. Quantum sensor technologies, there are huge projects being given out to quantum computing, and so we could take advantage of that, and then developing labs. So possible, there are various ways we can envisage this happening. So it is clearly going to be something we do with international partnership. So we are open to investigating all options. ISRO led with substantial ESA participation, ESA led with substantial ISRO participation, possibly other partners. If US goes ahead, then yeah, or various forms. So this is up in the air, but these are the two things we are really looking at very carefully now. And we need to start a joint phase and joint study phase for this. This was the projected timeline. We shouldn't get into, this sort of tells you what we envisaged: 1 year of pre-mission, 9 years of getting there to launch, and then science operations for 6 years. That's what we projected. It's just suggestive and preliminary. I just also wanted to point to what exists in India. So we have set up in this consortium working groups, which are led by pretty reasonably well-established young people in the field now. And many of them are here. And these are the areas and people around it. And we actually sort of, for this mission design, we should say that we built upon very mature designs that were available already. This is a very mature field which we are getting into. So we are actually, sort of basing it on, sort of core and pixie ideas, and possibly now that PICO has come up with a thing, we would be happy to look at that. This is just a list of members in the working group, which I just want to say that there's a big community. We have over 100 people signed up to CMB Bharat. And a lot of them are actually in the areas of systematics, some into the instrumentation, and so that's where I will stop. So the last comprehensive CMB mission for temperature was done by Planck and launched in 2009. The question is, what would be the next generation CMB mission? I personally belong to the community, part of the community which believes a next generation CMB mission is the way to go to exhaust this field, which has been extremely successful over 50 years. And I hope this would be a part of it, ISRO would be a part of it. Thank you.
Great, thanks a lot also for being well in time. Questions? Rashid?
Maybe I missed, you did not mention angular resolution at 90 gigahertz, for example. What
angular resolution?
Yes, just to discover 50,000 clusters, you need angular resolution of the order of few arc minutes.
Yes, so it is of the order of few arc minutes.
Few arc minutes.
Yes.
Yes, and then could you tell us a little more? You have 20 channels up to 90 gigahertz, and this is just Michelson spectrometer, therefore it will be plus, plus, plus.
No, we are not putting in a spectrometer. This is an imaging telescope. It's an imaging capability here. So we have bands, which I can go back to.
Show bands, yes.
Yes, so. Yeah, so if you see, we go from 60 gigahertz to 900 gigahertz in about 22 bands or something like that.
This will be just filters, yes?
Yes, just filters. No spectroscopy. We actually, in the original proposal, we did put a small spectrometer going from 30 gigahertz to 3000 gigahertz, 3500 gigahertz. But from the feedback we got, we felt that trying to push two things together may be much more challenging than what we are already putting in. But if you notice, this is based on recommendation by Rishi, who is kind of a spectral distortions person.
Rishi,
he may want to put in an onboard blackbody calibrator so that the imaging capability can be also translated into some kind of spectral.
Thank you. Very interesting.
Lower frequencies.
Yeah. Oh, even lower than 60, you mean?
Lower than 60.
Okay. So that's what PICO is proposing? Okay, good to know that. So as I said, we'd be happy to have the feedback. Yeah, Subha?
So you mentioned the wet mass would be around 2 tons, which sort of maxes out the, I guess, the PSLV rockets with the various variants. Is there any sort of advantage to, like, would ISRO prefer something that sort of, would pushing it over the threshold of 2 tons, requiring a bigger rocket, make it less appealing or more appealing? Is there?
So we went with what we think ISRO can launch with Mark III, GSLV Mark III, not PSLV. And so this is the largest launch capability at this point.
Yeah. But 2 tons does come within PSLV with the XL variants, right?
It does. But the point is PSLV would not take you to the transfer orbit to go to L2.
I see.
So it's GSLV which will take you there.
I see.
With 2 tons. So GSLV can go to where PSLV goes with 4 tons. So GSLV can take bigger satellites, but not that far.
Let's thank Tarun again and.